In this lecture, we shall learn how integer numbers are represented and stored in a computer's memory. An integer number is a whole number which consists of 0, all positive whole numbers, and all negative whole numbers. It does not contain any fractional part. In computer science, a number which is only positive is called an unsigned number. In unsigned number, there is no sign involved as all numbers are positive in nature. There is one more type of a number called a signed number. In signed numbers, sign plus or minus is also involved as it accommodates both positive and negative numbers. First of all, let us talk about unsigned numbers, all positive numbers. As all numbers are positive in nature, we do not worry about the sign. How do I represent plus 3, or we simply write 3 in binary form? We have already learned decimal to binary conversion in one of our previous lectures. We simply divide 3 by 2. 2 times 1 is 2, the remainder is 1. Now we divide 1 by 2. 2 times 0 is 0 and the remainder is 1. We stop here as the quotient has now become 0. Catch hold of the remainders from bottom to top. This gives us the answer as 1, 1. That is, unsigned number plus 3 is represented as 1, 1 in binary. If I want to represent plus 3 using 3 bits, then I need to prefix 1, 1 with 0. It becomes 0, 1, 1. 0, 1, 1 and 1, 1 both are the same. They represent plus 3. How do I represent plus 3 using 8 bits? Just prefix 6 zeros to 1, 1. It becomes 0, 0, 0, 0, 0, 0, 1, 1. Say we are interested in representing unsigned numbers using a 3-bit long binary number. We can represent 2 to the power 3, that is 8 unique numbers with 3-bit binary numbers. The 8 binary sequences are ranging from 0, 0, 0 to 1, 1, 1. 0, 0, 0 is used for representing decimal 0. 0, 0, 1 is used for representing decimal 1. 0, 1, 0 for decimal 2. 0, 1, 1 for 3. 1, 0, 0 for 4. 1, 0, 1 for 5. 1, 1, 0 for 6 and 1, 1, 1 for decimal 7. This means using a 3-bit long binary number, one can represent 2 to the power 3 equals 8 unsigned numbers ranging from 0 to 7. 7 is nothing but 2 to the power 3 minus 1. In the same way, with 8 bits, one can represent 2 to the power 8 equals 256 unsigned numbers ranging from 0 to 255. 255 is 2 to the power 8 minus 1, that is 256 minus 1. If there is n-bit long binary number, then we can represent 2 to the power n unique unsigned numbers ranging from 0 to 2 to the power n minus 1. Things get a little tricky when we try to convert a signed integer number to its binary form, as here we need to take care of both positive sign and negative sign. To understand how a signed number is represented in binary form, let us take an example of a 3-bit long binary number used for representing signed numbers. With 3 bits, we can assign symbols 2 to the power 3, that is 8 signed integer numbers. Out of 8 signed integer numbers, 4 of them are positive and 4 of them are negative. The 4 positive numbers are 0, plus 1, plus 2 and plus 3. The 4 negative numbers are minus 1, minus 2, minus 3 and minus 4. Let us see how these 4 positive and 4 negative numbers are represented using binary. All positive numbers start with binary 0 and negative numbers start with binary 1. So these 4 binary numbers shall represent positive signed numbers as each of them start with 0, and these 4 binary numbers shall represent negative signed numbers as each of them start with 1. Positive numbers are quite easy to represent in binary form. Decimal 0 is binary 0, 0, 0. Decimal plus 1 is binary 0, 0, 1. Decimal plus 2 is binary 0, 1, 0. And decimal plus 3 is binary 0, 1, 1. Now how do I represent a negative number? Say, how do I represent minus 1 or minus 2 in binary form? Negative numbers are represented using 2's complement notation. Now what is this? Don't worry, I shall explain. First, we need to understand what is 1's complement of a number. Say you have got a number 0, 0, 1. Obviously the binary number 0, 0, 1. 1's complement of 0, 0, 1 is nothing but 1, 1, 0. What did I do here? I just inverted each bit of 001 as in case of NOT gate. 1 becomes 0 and 0 becomes 1. So 1's complement of 001 is 110. Now what is 2's complement of 001? It is simple. 2's complement of 001 is equals to 1's complement of 001 plus 1. So 2's complement of 001 is 110, which is 1's complement of 001 plus 1, which is equals to 111. So we say 2's complement of binary 001 is binary 111. We know that 001 is decimal plus 1. We may now say 2's complement of plus 1 is binary 111. And one important thing to note here is that 2's complement of a positive number is its corresponding negative number and vice versa. That is, 2's complement of a negative number is its corresponding positive number. So 2's complement of decimal plus 1 is minus 1. We represent minus 1 as 111. Now how do I represent minus 2? To do this, find 2's complement of plus 2, because we know that 2's complement of plus 2 is minus 2. Plus 2 is 0, 1, 0. 2's complement of plus 2 is 1's complement of plus 2 plus 1. First, 1's complement of plus 2 is 101. 2's complement of plus 2 is 101 plus 1, which is 1 plus 1, sum 0, carry 1. 1 plus 0, sum 1, carry 0. 0 plus 1, sum 1, and there is no carry. So the answer is 110. So minus 2 is represented as 110. Similarly, minus 3 is represented as 101 and minus 4 as 100. Just note that minus 2 in 3 bits is represented as 110. How do I represent minus 2 using 8 bits? Here, I need to prefix by 1. How many ones? We add 5 ones to get the answer 1111110. This is how you represent minus 2 using an 8-bit long binary number. Just note that if it is a negative number, prefix by 1, and if it is a positive number, prefix by 0. Here we observe that with a 3-bit long binary number, one can represent 2 to the power 3, that is 8 unique signed numbers, minus 4, minus 3, minus 2, minus 1, and 0, 1, 2, and 3, ranging from minus 4 to plus 3. Let us represent the range in terms of our bit length, which is 3 in our case here, as each number is represented using a 3-bit long binary number. Lower limit minus 4 can be written as minus 2 to the power 3 minus 1, which is equivalent to minus 2 to the power 2 equals to minus 4, and upper limit plus 3 can be written as plus 2 to the power 3 minus 1 minus 1, that is plus 2 to the power 2 minus 1, that is 4 minus 1, equivalent to plus 3. Similarly, with n bits, total possible signed numbers are 2 to the power n, and the range is minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. We have just replaced 3 in the previous example with the variable n. That's all in this lecture. I hope now you are clear on how to represent a negative as well as a positive number in a binary form.